Hey, everybody. Welcome. I'm going to get started now. For those who are drifting in, there's a few aids here for the workshop, some paper aids in the middle tables in front of me. You're welcome to go grab stuff, and people nearby know what you need and stuff. So I'm going to do a presentation before we get started. I'm going to try to kind of explain what we're doing and give you enough that you can start kind of fooling around and stuff. And then the second half of my presentation is kind of like some rambling far future stuff where I'm going to try to inspire people in the audience who are mathematically inclined to help extend this. So the idea here is that I have a project called Codex32, which is about doing computations on Bitcoin secret keys using paper computers, no electronics. And the motivation, which I'll talk about more, is to have long-term Bitcoin secrets where you don't need to trust computers long-term, basically. You don't have this ongoing trust requirement with hardware wallets and with side channels and bugs and all sorts of stuff. But the real holy grail of this kind of a project, you might imagine, is that you could have a hardware wallet where every single computation is being done by hand, right? Where you just generate your keys by rolling dice, you generate some addresses by doing some worksheets and filling the stuff out and spinning wheels. You receive coins to those, and then you can send coins by producing signatures also by spinning wheels and stuff. We are not there. We cannot do that, as far as I'm aware. So the moral of this workshop is that there's a huge class of computations that we do in Bitcoin that can actually be done by hand in a practical way. And we're going to do one of these. We're going to verify some best32 addresses in this workshop. And I have two goals here. One is to show you that this is true and hopefully work through a complete computation and inspire you to check out the full booklet, which explains how to generate secrets, checksum them, split them up, recover them, all that good stuff. And the other goal, as I said, is to try to inspire people to try to push the envelope here and see how far can we go. Can we go from just having a way to have long-term storage where we split up our secrets and can verify their integrity with checksums without computers to a situation where even at the edges, even when we're generating addresses to receive coins and generating signatures to spend them, we still don't need computers. That's the dream. So let's jump in. I'm going to skip this slide because this year there is not really a FedEx store nearby, Belay. And we have not run out of equipment. But if you need, you can, all this stuff here. So every single slide will have this URL at the bottom, secretcodex32.com/tab6. On secretcodex32, you can download these slides. You can download all of the full booklet that I'll talk about. All the worksheets that you need, all this good stuff. You can download this all and do it at home, okay? So this is all open source. We do have these very nicely printed booklets that I'll wave around at several points that you can buy on the Blockstream store, but you can also just print them yourself at home, okay? It's all available. So let me jump into things. So let me start. I have a few slides just kind of explaining what this whole project is and trying to motivate it, right? So first off, all right, you can maybe tell from the abstract and the description, what are we doing? We're doing computation using paper computers. Why do we want to do that? Well, it's difficult to trust electronic computers. And with Bitcoin, somewhat uniquely, we have a whole set of keys that are very high importance. You have keys where if you lose them, then you lose your coins and you never get them back. Or if they're stolen and bad people have copies of them, then they're stolen and you lose them and you never get them back. And if you're not regularly moving the coins, then you have these single keys sitting out there that have that need to survive for the long term without being stolen or lost, basically. And this introduces, well, this is already, even if you're willing to use electronic computers, right, quite a difficult problem historically. Like most cryptography does not have these kind of long-term key integrity requirements. It's pretty rough. But adding to that, we have this long-term trust requirement for the hardware wallets that we use to manage your coins. And even if you don't trust hardware wallets, if your team like ThinkPad from eBay from 1998, which is a good way to do things, right? your hardware will fail over time. If you have Bitcoins that you're trying to store for decades or for centuries or something, then in order to verify that your coins are there and that they still work, you're going to need to have our hardware wallet and keep it reasonably updated. At the very least, you need to replace it when it breaks, but arguably you should be updating it, and arguably you should be just like replacing it with something that's maintained and has an active company and stuff. And over the years, these things change, things change. It's just an ongoing trust requirement. Or more than an ongoing trust, it's a new trust requirement, just constantly new trust requirements over the years. So the idea here behind the Codex32 project is, what if we don't have to use electronics at all? Okay, and there's a number of reasons not to trust. So not only is this trust requirement ongoing and constantly being refreshed, it's a big trust requirement. Okay, computers suck. You can't tell at all what computers are doing, right? You have a hardware wallet, it's got a little screen, you push some buttons, okay. Is it backdoored? I don't know. Is there bugs in it that are equivalent to a backdoor? I don't know. Are there side channels in it that would allow somebody monitoring your power or monitoring the EMF waves near the device to read what it's doing? I don't know. If you generate keys on it, are those keys uniformly random? I don't know. Are they uniformly random but somehow tweaked in a way that that would allow somebody to extract them with like an HMAC or something? I don't know. There's a lot that you don't know. Some things you can answer, right, if you've got some decapping equipment, an electron microscope, and all that good stuff. So that's great. But a lot of stuff you can't, even with that. So computers suck. If we can avoid them, that's great. And for the specific use case of long-term keys that you aren't using but want to verify the integrity of, we can avoid computers. That is the message of Codex32 here. Thank you. So, as a quick overview of what the workshop is, and I'm going to try, I've got like a presentation that I could easily spend like 6 hours babbling about, which I won't do to you, but I will periodically like double back and remind you that there's a workshop happening and here's what you can do. And if you want to just play with the things in front of you, you're welcome to work through it. It's an open workshop. I'm not sure what else is happening here right now, but you're welcome to come, you're welcome to go, and you can kind of get caught up pretty quickly. Unlike past workshops, I've reduced the scope here. So you just need two things. You need an addition wheel, which is the wheel with the dragon on it. There's some in the oh wow, okay, they're all gone. So you might have to share an addition wheel if you're coming in. And you need a worksheet. So you'll see there are these three quick check worksheets. They're labeled 1, 2, and 3. They're all equivalent in a certain sense. They'll all give you the same assurance, but you can just pick one and go with it. The reason there's 3 is kind of a neat mathematical reason that I'll talk about. So the only two things you need is a single worksheet and access to an addition wheel. And if you don't have the addition wheel, by the way, there is an equivalent lookup table at the beginning of the booklet, so you can go on the secret Codex32 website, download the PDF, and use that lookup table instead. Because ultimately, what this little wheel in front of you is doing is it's just a lookup table. And it's doing something called addition in the field of the 2 elements. So in past workshops, I've tried this really ambitious thing where I would bring in the entire booklet, and I'd say, let's work through this whole stupid booklet. And it's pretty thick. It's pretty thick, but like most of them are the same page repeated 80 times. There's a lot in it. So what the booklet can do, and what I encourage you to download and or buy this and play with it, it will let you generate new secrets by rolling dice. And dice are often biased. So if you buy a transparent dice, you will see, if you look closely, tiny air bubbles in them. Well, the more expensive the dice you get, the less likely there will be, and the smaller they'll be. If you buy normal, like the kind of dice that come with your Monopoly board, I promise you there are air bubbles in them. Because it's just, when you're manufacturing dice, right, it's not super, if you're doing it cheaply, right, it's not a super precise thing. And that's just a manufacturing defect. If you've got dice in your house and people know that you're using them to generate Bitcoin keys, imagine you could be having a dinner party, right? And your evil house guest will sneak your dice into the oven, which is still warm, and leave them there facing all ones up, thus causing the dice to melt slightly, biasing them towards showing more ones. They sneak the dice out, you never know. They feel a little warm, maybe it's the warmth of your hand. I don't know. There's a lot of things you can't verify in this world. So there is a worksheet in the Codex32 booklet that will debias these dice. It's a little bit tedious and time-consuming, but it will eliminate any what's called first-order bias in the dice, meaning that if they tend to show certain numbers more often than others, it will erase that and produce uniformly random things. If there's second-order bias, where like they tend to show the same number over and over, there's not much that the worksheet doesn't prevent against that. That's generally pretty difficult. If you're rolling the dice well, it's pretty difficult. Somebody would need to put some like really crazy electronics and gyroscopes and stuff in them to do something like that. In the interest of time, I won't continue this train of thought. Okay, you can generate random seeds. You can then compute a checksum on these seeds. For those who don't know, a checksum is a little bit of extra redundant data that you stick on the end of some data, and it provides some assurance that the data is intact, that there haven't been any errors, so no characters have changed along the way. And checksums have kind of this neat property that if there are, they have what's called a design distance, where up to a certain number of errors, they are guaranteed to detect that the errors are present. And in fact, they can even correct a couple of errors. So in the Codex32 book, we have a checksum called Codex32. It adds 13 extra characters to your data. If you have up to 4 mistakes in your data, even if you don't know which characters are wrong, Codex32 will let you figure out what the correct characters are and fix your stuff. If you do know which characters are wrong, it can do up to 8, by the way, so that's kind of a cool thing. Okay, so we generate checksums. We also do something called Shamir secret sharing, where you have a single secret, and you split it into what are called shares, multiple shares. And you need a certain number of those shares to recover the secret, but if you don't have that number, you learn nothing about it. And so, for example, you can split it up into, say, like 10 shares, and you need 3 of them to come together to recover your original secret. So you have these 10 shares, you distribute them to your friends and family and lawyers and banks and whoever, and they individually are unable to steal your coins because they would need to have 3 of your shares together in order to do so. But also, you have a fair bit of redundancy, right? You would need like 7 of them to lose their stuff before you lose access to the thing. So that's pretty good. And kind of a neat feature of the checksums that we work with is that they're compatible with the secret sharing. So when you split your secrets, if your original secret was checksummed properly, the shares will automatically be checksummed, which is great because, as you are going to find out, it is very tedious and annoying to do these long computations by hand. You'll make mistakes. And since you have a checksum, you'll be able to detect those mistakes and fix them, which is really, this whole system wouldn't be workable, bluntly, without that. So that's pretty cool. Okay, so we generated the checksum. You can also verify the checksum on all of your split shares. And the process that I would recommend for anybody using this is that they ask everybody who has shares, part of their secrets, to pull these out of the freezer or whatever every 3 or 6 months, like have a schedule, go through, do one of these quick check worksheets that we'll talk about in order to verify that the data's still intact, and then put it back and put a new tamper-proof seal or something on it. And the point of this exercise is that it gives you like a timestamp at which you know that the data was intact. And it also gets everybody holding the secrets to practice the process of digging them out, okay? Because there's a tendency with long-term cold storage, right, is that you put these onto into a crypto steel tube or something, and then you like drop that in a hole in your house or whatever, and then you forget about it, you know, and then maybe 6 years later you don't find it, and then 6 more years later it's just like in the back of the oven, and you're like, well, how did that happen? Did the kids do it? Did somebody open it? I don't know. There's lots of stuff you can't verify in this world. So you have a regular process. You check, you figure out where it is, you go through the process, you remember how to use the worksheets, you get some practice, put a new tamper-proof seal on it, and move on with your life. And now you have this long, and then you destroy the worksheets. So part of doing all of these calculations is that you have these worksheets like the ones in front of you. You need to put secret data on there, you do some computations with it, and then you need to securely destroy that. And unlike with a hardware wallet, where you really can't know whether any data is ever being deleted, right? Like even if the software is well written, like the flash chip, the like literal chip on the board could have wear leveling logic that is just preventing it from overwriting stuff you tell it to overwrite. Paper you can destroy securely. The kind of the obvious way to do so, right, is to just burn it. You can do that if you have a big fire, you like a fireplace, and you're running it for some hours straight. You can put paper in it. You can't just set a piece of paper on fire and throw it in the trash. There is a MacGyver episode in which a corrupt manager does that in order to screw over a union worker. And MacGyver is able to recover the burned data by using photo development chemicals. So I encourage you to look that up. I forget which episode it is. But anyway, fire is actually not so easy to securely destroy data. I spent some time trying to use like Magician's flash paper, which goes up in flame. It turns out you're not supposed to set fire to a whole 8.5 by 11 sheet of flash paper. That will, it creates a big fireball, it burned me, and it was not very practical. And it's really not, that stuff is scary, right? Like it comes like packaged, like kind of saturated with water and has all these warnings on it, and there's like there's like a fire code for stage magic. I didn't know this, what a country. That tells you like all these things you're supposed to do, and you're not supposed to like keep it for long term. You're not supposed to put it in a printer. When you're writing with it, right, there's always this like nerve-wracking feeling that maybe the friction from your pencil will cause it. Like, anyway, in real life, just use printer paper. I recommend you put it in your blender with a couple cups of water and run it, and it will turn it into a gray goop. If you add enough water, it'll be very liquidy. You can throw it in your toilet. It's not going to fuck up your plumbing. I guarantee it. And that's very thorough and very reliable. Sure? Yep. Oh, sure.
Every piece of mail I get goes through that shredder, so yeah.
Yep, no, that's a good point. If you've got a good shredder and you're using it constantly, that's
Not
realistically
one of these
that's probably
pathetic office shredders that make 4mm wide links.
Right. Yeah, no, I've got one of those. I mean, it also cross-cuts, but it's still not. You can still read the data with the shredder I've got at home. So, yeah, if you've got a good shredder, that's also reliable. But yeah, make sure use some common sense, right?
Where did the blender idea, was that original or is that like a known thing?
I think it's original. So I was using fire. I spent a lot of time kind of playing with fire. Yeah. Yeah, and like I was already in the kitchen because I was burning the flash paper in the sink because I'm not a madman, right? And then the blender was right there. So I'm like, well, what if I use that? So yeah, I think that answers your question. All right, cool. So there's all these different processes. They're super cool. They take a while to do. All right, so rolling the dice. So assembling these volvels, cutting them out and cutting out the little windows, that's close to an hour of work. It's kind of fun. I didn't want to do it in a workshop because it takes a lot of time and people get frustrated and they feel like they should be moving faster, but it takes a bit. Rolling the dice takes a long time to debias. Generating the checksums initially takes 45 minutes to an hour for your secret. And you kind of have to do it twice because when you generate the checksum, there's no, like you can't be sure that you did it right. So you kind of like have to redo the worksheet to verify it, which isn't very fun. And then if you do make a mistake, you've got to double back and fix that. So, and then splitting is not so bad. Once you've got everything working, splitting takes like 10 to 20 minutes per share, and then recovering takes 10 or 20 minutes per share. And it's very late. It's a lot to go through in a workshop where people are learning this for the first time and we're trying to stay in just a couple hours. But I encourage you to get the worksheet and like if you've got a spare weekend, get the full booklet, and if you've got a spare weekend, you can play through all of this. So, all right. So, in this talk or in this this workshop, we are going to just do the one thing, just do one verification step. Okay. So I'm going to skip over Volval assembly. So I would like to thank the several volunteers who came and sat down beside me over the last 4 hours and helped me cut out all of these little wheels. There are 25 of them. Thank you. We don't have to do that. And then I'm going to jump into my explanation of quick checks, which are the thing that we're doing. And I'm going to try to do that in like 10 to 15 minutes so that we can get started. And then I'm going to kind of like keep talking, and you're welcome to tune me out. It's going to get technical, but it's not going to get relevant. So it's not, yeah, it's cool. I'd like to try to get started. Cool. So quick definition. I've been using this word volval, I think. A volval is a term for these paper computers, these rotating paper computers. We've got two sheets of papers. Wikipedia claims that these date to the, I think, 10th or 12th century for astronomical purposes. I kind of suspect that they date much earlier than that. But there are these kind of rotational star charts that you can find that have been around forever and ever that are basically volvals that are computing the position of stars by rotating things. There, as recently as the 1980s in the US, you could purchase volvals at any gas station in California This is a Murray's dial a mile of California. You turn it so it's pointing up top to the city that you're trying to go in, and then there's a bunch of little windows on the front that will show you the number of miles you need to drive to get to that city from all these different places. Okay, and we drew some inspiration from this Murray's dial a mile, so I was quite thrilled when somebody put one on Craigslist near me for only $7, because that is an antique piece of Volvo history, so very fortunate to have it. Checksumming, as I say, you add some redundant data, then you can detect errors, and it's kind of cool because they're really flexible, right? You can detect errors, multiple errors, even if you don't know where they are, anywhere in the string. Secret sharing, splitting up your data, recovering them. We're not going to do that in the interest of time, so there we go. So let me give a quick update on where we are with this overall project, right? So as I said, we can compute and verify checksums, we can split and reconstruct secrets. I've said that you can correct errors, but doing so by hand is pretty difficult. I know how to do it with like an algebra textbook beside me and working through all of the math, but I don't have a set of worksheets or a good process for it that I haven't figured out. There also isn't really a way to do hashing or to derive multiple addresses from a single secret. That's not too bad. There are a number of hand computable hashes out there that we could evaluate. I think any of them would probably be sufficient for this, but I haven't dug into that too much because the big thing is we can't derive addresses or signatures. There's something called an elliptic curve multiplication you need to do by hand, and it's very difficult, and I'll talk about that later. Okay, that was 2022 when I last did this talk here. 2024, we have some improvements. So one thing, we can correct up to 1 or 2 errors. The checksum itself, as I said, can correct up to 4, 8 if you know where they are. Well, we can correct 1 or 2 just by using lookup tables. So the idea here is at the end of the worksheet that you do to verify the checksum, you're supposed to wind up computing the string secret share 32. Should show up magically at the bottom. If it doesn't, something else will show up, and you can look that up in a lookup table, and it will tell you, based on the thing you computed, exactly which column your mistake had to have been in, and what you need to do to fix it. So that's kind of cool. We think we can do full error correction. As I said, like the algorithm's not too bad. It's tedious, but the hard parts are pretty repetitive, so I think we can find a worksheet for it. I believe I can do partially blinded address generation and signing, and again, I'll circle back to that later in the talk once I've got everybody moving. So we are making progress. This is an ongoing kind of multi-year journey, and it's certainly not done. So I'll leave this quick overview slide up for like 30 seconds in case people want to take pictures of it. It's got a couple of URLs. The website, Secret Codex32, that really has every other link on it. That's all you need to know is secretcodex32.com, which is at the bottom of every slide here. But there's a couple other things. As I said, the project's not done. You can email Perlwert, is one of the 2 authors of this. Perlwert is me. I shouldn't dox myself, but I have done a very poor job of hiding that identity, so I'm just going to say it. Shoot me an email, especially if you think you can extend this, right? But also, if you're just using it and it's hard, if you have user experience feedback, I really enjoy the emails that I get to this address. Honestly, they're all so weird. So certainly, that's please feel free to do it. Okay. State of the project, can you actually use this for real coins right now? Well, in order to use this hand-computed process, there's a new format for encoding your secrets. So it's not like the standard BIP39 code words. So we need wallet support for it. We have like very sketchy wallet support. There's a closed PR to core, not merged, closed PR to core that you can resurrect and use. I will open a new one and like do the RPCs properly like they asked me to one day, I promise. There's a wallet called Bales, part of the Bitcoin on Tails Bales project, which I think uses that closed PR. So there you go. You can do it that way. And then I've been working on implementing error correction. It's mostly done in Rust Bash32, which feeds into Rust Miniscript, which feeds into BDK, which feeds into like half a dozen hardware wallets out there. So once I've got that together, that should give wallet developers the APIs they need to implement this, and you should be able to use it for real. Having said that, you can also kind of like sketchily coerce BIP39 words into this format and then just do everything that way and then coerce them back when you need to use it. I do this for my own coins because I really like this project and I think it's a dramatic improvement, but I'm well on the wrong side of inventing sketchy key management processes where I'm much more likely to lose my coins because I forget all the stupid stuff I did than I am to protect them from whatever imaginary threats. My threat model is a bit different, right? Because like I do a lot of public speaking, and people imagine that I have a lot of Bitcoin. So it's also helpful for me to like publicly say, even I don't know how to get them, right? So good luck. Mug me all you want. It's not going to help you. Don't do it. I did a talk at the MIT Bitcoin Expo in 2022. You can find, I think there's a link on the Secret Codex32 website where I ramble for quite a while. And that I think is kind of the talk explaining this project. So, okay. Assembly, we can skip. Tips for handwriting. So the worksheet in front of you, we're going to wind up filling out. I think we distributed a bunch of mechanical pencils. You can use a pen if you want, but it kind of sucks. You make mistakes, and then you can't undo it. Write clearly. Use capital letters. The one character I would say to be careful with for me is 6s and Gs. I haven't found a good way. You just got to be slow and careful to make sure your 6s and Gs look different. Cross your 0s, your 7s, your Zs. Also cross your S's so they look like dollar signs. That's what I do. And that makes them clearly distinct from 5s, which otherwise look pretty similar if you're writing sloppily. But so 5s and S's you can distinguish by crossing the S's. Although then you need to make sure the S doesn't look like 8. But that's a little bit. You'll just be careful, right? You'll get some feel for it. But that's my advice. Here's a picture of the 3 volvels that we use in the full worksheet. The middle one is a dragon volvel that you have in front of you. This is a old red revision, which looks pretty cool. I'm not certain why we changed it to green. I no longer we did a lot of iterations on the art, and I don't remember how this happened. The other 2 are fusion and recovery. Those are used for secret splitting, but for checksum generation and verification, we don't need it. So we only need the dragon volvel for this. But they all look pretty cool, and they're together. The one that is on the left there is double-sided. You can flip it over. I don't have one in front of me, but it's double-sided. It's kind of cool. You use one side to like rotate it to a certain position, and then you flip it over, and it acts like a decoder ring. If any of you are 10 years old, you can use that to encrypt messages to your friend. Do kids pass notes? I don't know. But you can use this volvel to do it. The teachers, I promise, will not be able to decode it. Tell them to email porwart@secretcodex32.com if you get in trouble. They can talk to me. This is me and my now wife. She gave me a wooden version of the edition volvel for Christmas, so I married her. So, there's lots of good things thank you, that come from this. So, all right, I have a couple slides of theory that'll be a little bit heavy. You can tune out if you want. I'll try to be quick about them, but I want to kind of explain what it is that we're actually doing here. So, I mentioned all these magical features of checksums. Specifically, we are using something called BCH codes. Okay, and BCH stands for 3 people's names. 2 of them I can't pronounce, so I won't pronounce the third either. It's just three pioneers of coding theory in the 60s and 70s. The way that they work is that you take your data, mathematically speaking, and you interpret it as a giant polynomial. So you've got some like BC1Q, 1, 2, 3, whatever. You treat all of those letters as a kind of number of what's called an element in the field of 32 elements, but a kind of number that you can multiply and divide, and then you can create a polynomial on these. So if you've got the string ACDE, you imagine that means A times x cubed plus C times x squared plus D times x plus E, where these multiplications are happening in these fields. And then we're going to define a subset. This is how all error correcting codes work. You have a set of code words. And a code word is a valid string in the error correcting code. And the idea is that all of your code words are far away from each other. There are no 2 code words that you can get to by taking one and like flipping only 3 values. And so in Codex32, in fact, you can flip up to 8 values before you will get another code word. And so you can see then, if you flip up to 4, your original string is the closest code word in kind of this abstract space of code words. So you start with a valid code word, and you've got this like giant high-dimensional space around it that's empty of other code words. And the idea is to do error correction. You take a bad string, you assume that only a few errors have happened, and then you kind of snap it to the nearest lattice point, which will be the original string, assuming only a couple things happened. So you produce this lattice by having multiples of a specific object called a generator polynomial. And so the whole concept here is that we're going to be taking our strings, interpreting them as code words, reducing them modulo the generator polynomial, and making sure that we get 0. Or actually not 0, a fixed offset, but morally 0. Just making sure we get a fixed value. Okay, that's pretty abstract. I'm going to continue to be abstract for one slide, and then we'll see that this is actually super easy to do. So to checksum, well, you have a bunch of data. It's some random string, right? It's a random address or secret word or whatever. It's not going to be a code word because it's a bunch of random data. How do you make it a code word? Well, if you've got a generator polynomial of degree 6, you can multiply your string by x to the 6 and then just add some extra crap at the end. And you can choose that extra crap so that it will cause the entire string to be a multiple generator, okay? So that's kind of what you're doing. That's why we think of a checksum as you adding some extra data at the end. What you're doing is you're actually mangling your string in order to be a code word, but you're lengthening it first so that you can mangle just this extra data that isn't part of your real data. To verify, it's pretty straightforward. You've got the already extended and mangled data. You just reduce it by the generator, check that you get the fixed value, okay? So in best32, the fixed value you get should be 1. In best32m, there's this different random constant. It turns out that 1 has some bad properties. In Codex32, you get a 13-character string that when you write it out, spells out secret share 32, because we, as designers of the code, can choose whatever offset we want. And we chose one that was visually kind of interesting. Okay, so, all right, so in order to verify a checksum, I'm saying you interpret, you get this giant polynomial, you reduce it modulo another polynomial, like, oh my goodness, what is happening here? Well, if you were implementing this by computer, you would use something called Horner's method, where rather than starting out with the whole giant polynomial, you just build it up character by character. So rather than starting, you start with just like the constant 1. You multiply by x, you add the next character, multiply by x, add the next character, multiply by x, add the next character. You can convince yourself that this will produce the original polynomial. But the cool thing is that at every stage, you can do the reduction. You multiply by x, add the next character, then reduce. And this means that if you're reducing by a degree 6 polynomial, for example, your whole string will never be more than 7 characters. And if you're, I know I'm in the weeds here, but I promise it's going to come out to a simple worksheet. And you only have one character kind of at the end, which needs to be reduced. The kind of neat thing about polynomials is that if you're reducing by a degree 6 polynomial, then the bottom 6, the least 6 significant coefficients won't change. They just stay the same. So you have a 7-degree polynomial. Only the top coefficient actually matters. Well, there's only 32 possible values for that because you're in a field of 32 elements. So rather than computing this reduction, which has some complicated mathematical definition, you can just look it up in a table with 32 values, okay? And then you can do reduction that way. And what we're going to do here, we're actually going to do 2 characters at a time. We are going to add 2 characters to our polynomial. We're going to wind up with these 2 extra dangling high coefficients. We need to reduce those. Well, how do we do that? Well, there are 1,024 32 squared possibilities for those top 2 characters. So we have a worksheet. We have a table in front of you with 1,024 entries. All right? And so we're going to do addition. The 2 things we need to do are addition, which we can do with this addition volvel, and reduction, which we can do with a lookup table. Okay? All right, I lied. I have one more slide of technical stuff, but I'm going to rush through it. So best32 has a generated polynomial, which is degree 6. And that means that you have 6 extra characters that you need to add at the end of your stuff. And it means that if you're doing a checksum verification by hand, you'll have this giant kind of diagonal-looking worksheet, which requires you fill in the length of your data times 6. It's a lot of extra work. You don't know until you're done whether you messed it up or not. And when you find that you've messed it up, you can't tell where you messed it up, so you just have to redo the whole thing. It's super tedious. It turns out we can do something easier. Rather than reducing modulo this degree 6 polynomial, we can reduce modulo a degree 2 polynomial, which is a factor of the degree 6. So it turns out that the best32 polynomial factors into 3 degree 2 polynomials, 3 quadratics. And it's equivalent by something called the Chinese remainder theorem to reduce your data modulo the real generator, or to reduce it modulo all 3 of the small generators. And that is why there are 3 different quick check worksheets out there, is each one is doing a different piece of the full best32 checksum. And the cool thing here is that while it's equivalent to do all 3 of them, that's equivalent to doing the full thing, and that's already an improvement because the small ones are way faster. So if you mess them up, you can redo them in 5 minutes instead of an hour. What's cool is even if you just do one of them, that gives you high assurance that you don't have errors. So you get kind of this incremental improvement. And that's why I told people you really only need one of these worksheets in front of you. It doesn't matter which one. If you want to do a full verification, you can do all three. But even doing one of them will give you, if there's a random error anywhere in your string, you'll detect it with a 99.9% probability. 1,023 out of 1,024. OK. All right, it looks like everybody's got stuff, so I can jump over that. So now we will get into the workshop, and people can start writing. I will continue to talk for quite a while, but feel free to interrupt me. Feel free to ignore me. Feel free to start playing. Because after this slide, which I will double back to if and when I finish, the rest is going to be kind of like future work and stuff. So how do we do this? So first off, you need a Bitcoin address, OK? And you can, so I considered giving you guys an address, but I wanted to kind of demonstrate how cool this is. So you guys can get your own Bitcoin address. You can pull out your phone wallet or just go on any block explorer or whatever. You need a SegWit address. It has to start with BC1Q. For the Taproot address, it'll be too long for this worksheet. And the checksum is slightly different. If people are struggling with the internet, I did grab one out of the Rust Bitcoin unit tests that I can tab over if people want me to. Or you can, but hopefully enough people can get one and you can like copy it from your neighbors or something. I mean, these are just addresses, they're public. So what you're going to do is you're going to write out your address in the bold boxes. So in the worksheet, you'll see there are kind of 3 rows here. And the middle row has bold boxes. And that is where your secret data goes. Except here, we're not using secret data, we're using public data. We're going to use addresses. OK? And what we're going to do is verify the checksum on these addresses. And just to kind of demonstrate how checksum verification works. And to do something that we can do in the space of 2 hours. Or in the space of an hour and 15 minutes. OK, that's the first thing. The second thing is going through all of these. Oh, thank you. Going through each of these pockets of 2 characters, we are going to add the top 2 rows together to get the bottom row. And then we are going to look up the bottom row in the table in order to get the top row of the next triplet. OK? So in the example here, right, so we start out by writing, we've got our address here is QYA. The BC1 is already filled in, and it just kind of floats there. It's something special called the HRP. We fill in our data. We have 9. The first character is treated specially, so 9 just goes to 9. We have F. Well, F plus Q equals F. And you can spin, if you want, on your addition wheel, you can spin it either to F and look up Q, or you can spin it to Q and look up F, and you will see that the result is F. In fact, you will see that adding Q to anything just gives the same thing. Q mathematically equals 0. So when you're doing addition, it doesn't change. OK, so F plus Q equals F. We get 9F at the bottom of this first pair of columns. And now this 9F, this 9F secretly represents these like extra high-degree coefficients that we need to reduce. We're going to reduce them. How do we do that? We use the lookup table. So we look up 9F in the lookup table. And those of you with Quick Check Worksheet 1 can verify that 9F in the lookup table gives you EH. So we're copying this 9F. We look it up. We get EH, and we put EH in the top of the next pair of columns. And now we can keep going. We can add EH to YA to get A2 at the bottom. We look up A2, we get 6W. And then we would add 6W to PU, and we would find, well, I don't have a wheel in front of me, but we would figure out whatever 6 plus P is and fill in that bottom box, and we would fill in whatever W plus U is and fill in the bottom box. Look up, repeat, right? So we're adding, looking up, repeating. Those 3 steps over and over. Yep. Oh, yes. Yep. Yep, exactly. Yeah. So you're looking up. So the bottom 2 rows, you're looking them up. Those will be the black columns. And to the right of the black column is what you're copying out. So in the full booklet, you will see if you are doing, rather than doing a quick check, you're doing a full checksum verification. You will see you look up 2 values and you get 13 out. And so in that case, this table it's much clearer how to read it, right? You have 2 values, you can just look up 2. Unfortunately, with lookup tables, if you're looking up 2 characters and getting 2 characters out, it's just hard to make clear what's the input and what's the output. But you're looking up stuff in the black columns, you're reading it out of the light column to its right. And so there we go. And if people who are like user interface designers or graphic designers or anything, if you guys have suggestions or if you think you can do this better, again, please email me or talk to me or something. We really want to make this clear and usable. And this is not my specialty, doing this kind of thing. So it's a learning curve, and I would appreciate any feedback. So does this make sense to people? Are there more questions? Yep.
Clarify. So 9F goes in the above, so you have YA next. But for me, I have 9-0.
Which quick check worksheet do you have in front of you?
Quick check 1.
Okay. Let me pull up the doc and.
Yeah, I did that.
I mean, I have worked quick check 1, and the keys are the black ones, and the values are the other ones, the blue or the white ones. So
Let's see. So I look up
9F, EH, see?
Yeah, it's the step after that.
Let me zoom way in here. Oh, that's the other one I want. F. I get EH. So you guys can see.
No, it's the other one, the next one.
Oh, the next one. Okay.
You need to go back to your slides.
Here. Okay, so we look up A2, and I should get 6W. Yeah, okay, it's 6W. I see it down here. So on quick check worksheet 1, this is number 1, right? Yeah. A2 goes to 6W. So I think. Oh, sorry. I think we're okay here. The one kind of weird thing is that on the worksheet number 2 and worksheet number 3, there are different tables.
Hey, quick sanity check. So we write out the whole Bitcoin address through the middle row.
Yep.
And then I noticed I have quick check 2. I noticed the very final numbers are sort of ghosted in. Are those the
Yep.
numbers I'm supposed to be expecting? And then that's how I know I did it right? Or
Yep, exactly.
and then no matter what, the idea is no matter what address I pick, I'll always end in DR.
Correct.
For
Yep.
me.
Yep.
This sounds like magic. I don't
Right,
get
it does, yeah. And I'm telling you, to look up any address, right? Look up one that like you just generated, and I promise you, you will get in worksheet 1, you'll get AN, in number 2, you'll get DR, and in the third, you'll get EW, which spells my name because I can generate these worksheets to have whatever values I want.
So
And yep,
I'm on quick check 2 as well.
yep.
I just put in a receive address and it's short by 1 digit.
Sorry, say that again? The length is wrong?
Yeah, am I using the wrong address?
You might be. What are the first 4 characters? BC1Q?
Yeah.
Okay, but it might be it might be like a script address. Yeah, shit, sorry guys. It has to be a key address, which is a short version of SegWit addresses.
So my address is
it's
1
really
short
frustrating.
than the number of boxes.
No, there's a big yeah. If you're missing 1, then you
I
you messed
double
up. Yeah.
checked. No, I
Yeah.
double checked.
If you're missing a lot, though, you might have a long address instead of
No,
a
no,
short
no.
one. Right. Sure. Yeah. All right. So let me quickly fill out the worksheet up top. All right, now, guys. So here's the magic of PostScript, by the way. So I would like you to behold that I just computed this entire worksheet in PostScript, which is a Turing-complete language in which I have implemented the entire process. And my colleague also implemented a handwriting-like font there that kind of fills everything in. So here is the address from, this is in my local copy of the document. So here I filled in the entire worksheet with the address that I got from Rust Bitcoin. It's BC1QYAPUVA6G, so on. I'm reading the middle things. And you can see that after taking a short address and dropping the BC1, but still including the Q, which is pre-filled, it fits exactly. I don't wind up with extra characters. If you have a long address or you have a taproot address, which is also long, which is also 256 bits long, it's not going to work for you. But it fits exactly. And then you can kind of spot check if you want that all the table lookups work out to what they're supposed to on Quick Check Worksheet 1. And then the final value is AN, as it's supposed to be. So yeah, I'm not sure what's that. So I'll leave this up for a couple minutes while people ask questions.
Okay, so I get everything. I'm going pretty quick here. This is so fun. But my question is about the error correcting capability here. So let's say I get all the way through and don't get DR.
Yeah.
What's the process exactly for understanding where I messed up?
So the process would be that you redo the worksheet. So if you know the address is right because you just copied it off of somewhere, you should double check that you copied it and then probably just redo the worksheet and cross check. In general, if you pulled this out of your cold storage or whatever and you get the wrong value, the quick checks can't correct errors. So what you would do is you would do the full worksheet, which looks kind of like this. Okay, so this is the full checksum worksheet. This is structurally the same as the worksheet that's in front of you, except that rather than doing 2 characters at a time, we're doing 6 characters at a time. We're maintaining this giant polynomial. At the bottom, we get this value. For best32, it's QQQQQP. For secret Codex32, it's secret share32. For best32M, it's a different value that I don't have memorized. You can look up that value. And I've got an error correction table sitting around somewhere that we'll release as an expansion pack to the booklet. You can look up that value, and it will tell you which column and what value you need to add to the character in that column using the addition wheel, and then you can correct it that way. Yeah, we're not going to do that here. So in this case, if you don't get AN or DR or whatever, then you messed up the worksheet. And the most straightforward thing is to just redo the worksheet. Yep.
I'm sorry, I came in a bit late, but the point of all of this, yes, thank you. The point of all of this is to always get the same value in the end. You're always supposed to get AN no matter which value you put in?
Yep, exactly.
I see.
Yep.
And
For every
see.
valid address, you will get that value.
Okay, and with the other one, with the full worksheet, you're always supposed to get QQQP or something.
Yep, exactly.
I see. All right. Interesting. Thank you.
Yep. And that internally is what the computer is doing when it verifies this. The neat thing about this algorithm is that it is actually almost identical to what's being done, to what's implemented in C and in all the other languages. It's using Horner's method and gradually reducing this way. And it's even kind of using lookup tables. If you look at the Python reference code for Best32, you'll see that every step it does this weird XOR with like these magic-looking values and then like slight bit shifts. And those magic-looking values encode a lookup table, more or less, for this. So it's kind of neat. It's pretty neat how similar this is. For this stuff, like what we're doing by hand and what the computer's doing are almost identical. Yeah. So by reduce, so what we're doing is we have a long string and we're trying to get this 2 characters out, right? AN, DR. So by reduce, I mean taking your entire string and just converting it to 2 characters. So the way that we're doing this is that we're starting with the first 2 characters, right, of our string, and then we add 2, and then we kind of compress it. So you can think of the bottom row as being the compressed state of the computation at all times. So column by column, you keep putting more data in, but you keep having only 2 characters to work with. Yep. Yeah, exactly. So yeah, so mathematically, yep. So mathematically what you're doing is when you go to the next column, you're taking your bottom row, you're multiplying it by x squared and adding the next 2 values, and then you're reducing modulo a quadratic, which means, well, your lower 2 coefficients are basically ignored, and your top 2 coefficients are reduced to some value, and you add that in. And that reduction step, I've just pre-computed all 1,024 possibilities in the lookup table. Yeah.
So this wizard, Andrew, at the very end, he seems like a smart guy, but how much do we trust him that he hasn't given us a codex Volvet that just doesn't work, or alternatively, all converges on his address?
Yep. So this is a great question, and I see we're at that part of the workshop now. So yeah, it's a great question, right? I'm giving you this worksheet, right? This giant booklet with these piles of tables of random-looking data, and saying like, just trust me, bro. There's nothing untoward in there. How can you trust me that it just works at all? Well, I mean, you don't. If it doesn't work, then stop using it. But how do you trust that I'm not backdooring it? Well, with the checksum part, it's kind of nice because there's no real output, right? When you're generating the checksum, you're taking your original secret data and you're tacking some extra data onto the end. And in the case of secret data, it stays secret. It's not like you publish the checksum somewhere where I could read that and like exfiltrate data out of it, right? The checksum stays with the data and it doesn't go anywhere, so that's fine. When you're verifying, there's no, like, you're not changing the data at all, right? You write it down, you fill it out, you get a result, which hopefully is correct, and you burn it. So there's nowhere where I would see the output. Now, when you get into secret splitting, then the trust model becomes a bit more interesting, right? So imagine that you have a secret and you split it into multiple shares, and you give me one of the shares. And I've promised you on penalty of mathematics that all of those shares individually have no information about your secret. But there, you kind of got to trust me, right? Like, you generated the share using this worksheet. Supposedly, you need 3 of these different shares in order to reconstruct the secret, and 2 are not enough. Well, in order for this to work, the property of correctness here is that if you distribute up to 31 shares, you can only produce 32 distinct shares. Then any 3 of them will reproduce your data. And there are 31 choose 3 different possibilities, which is on the order of 30,000 different combinations of data that all need to come out to the same secret. So if I backdoored it somehow to not be doing Shamir secret sharing, I would need to preserve that property. And I don't think that that's possible. I think the system is so overdetermined that it kind of ties my hand a little bit. Now, there is one way which my hands are not tied, which is, well, the underlying way that these shares work is that you have 31 shares that are not your data, and then you have a 32nd share, which is the actual secret. So maybe what I could do is gin up the secrets, excuse me, gin up the secrets so that something you think is a share and harmless is actually the secret, right? That could be a way of backdooring. So all I'd have to do is rearrange some columns in my lookup tables. Well, In the actual Codex32 scheme, the 5th character of your data is what's called the share index. It identifies what the share is. And mathematically, what that is a straight line. Okay, so you were doing polynomial interpolation of a straight line, you get a straight line. And that means that every share you generate is forced mathematically to have the correct index. And the index of the secret is S, right? When you see that S in the first character, that's like a huge red flag that you've got real secret data and not just a share. So if I were to try to rearrange columns so that you were producing a secret but you didn't realize it, well, the secret will be clearly labeled as a secret because it has this S in here. And again, and that will be true as long as I didn't somehow replace Shamir secret sharing with some other object that has the same correctness properties. And my claim is that that's not really possible, but I don't have like a security proof, right, that an attacker who gives you a backdoored booklet can't do something bad. One thing you can do, though, is you can read the source code. So the entire booklet is in handwritten PostScript, and you can regenerate it. Another thing you can do is you can honestly just reproduce most of this stuff by hand. The addition vowel in front of you is the trickiest one, because it's got 1,024 characters on it that are all kind of rotated in funny ways. If you don't like it, you can produce your own lookup table. So rather than doing a vowel that requires like precision printing and rotation and stuff, just use a lookup table. You can generate it yourself from the mathematics of GF32. This is all humanly verifiable, I guess, is my point. Every single lookup table, every single wheel, every single algorithm is something that you could come up with just knowing the best32 encoding and knowing the underlying mathematics. So it's all pretty overdetermined in a way that makes it difficult to backdoor at all. And then in addition to that, it's all pretty simple and easy to reconstruct if you know the underlying mathematics. And then finally, it's all implemented in handwritten PostScript, so you can read the source code and see how it's generated, and hopefully convince yourself. If I get into the like far future stuff where we're speculating about doing EC math and stuff, there are some new ways to backdoor things that are kind of fun that I can speculate about. But this stuff, there's really no room for backdooring. Cool. So I will double back to this slide whenever people have questions or get stuck or confused or anything. Oh, yeah.
Can the value you're looking up ever be a O, or is it always a 0?
It is always a 0. Yep, so there are no O's. So the alphabet, this comes from best32. There are no O's. There are no 1s except for the third, the BC1. No 1s after that. No O's, no 1s, no B's, because they look like 8s. And no I's, thank you, because they look like 1s. Yeah, so I and 1 are both dropped. The L's are always uppercase. You should always use uppercase for this stuff. But even in lowercase, L is the only thing that's allowed that looks like L. Could I ask someone to refill my water? Cool. All right, thanks. Sorry about that. Thanks. Cool. So yeah, I'll keep circling back, but at this point, I'm going to keep talking because I like to hear my own voice. And if you're interested in where we're going with this, you can tune in or not. But this slide is really the whole workshop. All right. So this is what our goal is. And I think, like if you're kind of well practiced, you can do this worksheet, thanks, in 15 or 20 minutes. If you're not, you can maybe expect that it would take about twice as long, in my experience. And then, of course, if you mess up, then you have to do it again. So that can take a little while.
Why is it not possible to do slightly earlier the error detection in this sheet, like halfway or something, as a very sloppy person?
Yeah, that's a great question. So what you're doing, you're kind of continuously reducing You're building up a whole string and continually reducing it modulo this generator. And while the entire string needs to be a specific value, all of the intermediate values are kind of random, and there's like no, they can take any value. Like every single bottom square except for the final two can take any value, starting from any value, depending on what your data is. So there is, is it a bug in Best32 that we stick it at the end? So this is pretty standard behavior with checksum, right? There are lots of different ways that you can do this. So we certainly could have implemented Best32, so we're interspersing the checksum.
That would be easier when you're typing it as well. So it tells you, hey, this is probably wrong.
Actually, I take back my agreement with you. Even if we did this, it actually wouldn't help. Because even if we intersperse the extra characters, or even if we don't add extra characters and just have like a prescribed way of mangling the data, until you sum the entire string, you still don't, like, your intermediate values will continue to not be reliable. Now, what you can do, and which we haven't really elaborated in a good way, is when you're doing the full checksum verification, the full 13-character thing, you can do a quick check in parallel, and you can basically take, like you've got the giant diagonal worksheet here, where, maybe I closed it, but that's, oh no, it was scrolling up here. So what I do when I'm working with this stuff is as I'm filling out this giant diagonal worksheet, I'll take all of these 6 characters, or in the full thing it's 13 characters, all these 13 character wide rows, and I will reduce them by myself using the quick check table on graph paper. And then I will verify that the row, when reduced, is exactly equal to the 2 squares that appear in the equivalent position on the quick check paper, right? And there I can actually get intermediate progress checks on the big worksheet. And that makes things much easier for me, but it's difficult. I haven't found a good way to explain that process, right? Because the target audience of the booklet and of all of these algorithms is kind of a functionary, right? It's like an estate lawyer or somebody who's like, you know, certainly like quite literate and willing to do tedious things correctly that take a long time, but not somebody who understands the underlying mathematics and can find weird shortcuts and connections like that, right? So, but this trick that I use, it really helps so much when doing these giant worksheets to have these progress checks along the way. Like psychologically, it helps so much because it's a really bleak feeling to spend an hour filling out this worksheet knowing that quite possibly you already fucked up and everything that you're doing is pointless, right? And you're just not going to know till the end. So kind of the point of these quick check worksheets is that they're so quick to do, and they are. And once you're practiced, well, I have 2 comments. One is once you're practiced, you can probably do them like twice as fast if you're doing them now. And another is that real secret data is actually shorter even than the short addresses, right? Like a secret secret BIP32 seed is 128 bits, or 12 words or whatever, versus these addresses, which are 160 bits. So for me, I can do a full quick check worksheet in about 10 minutes. And
Would you like to use mine as an example to see what I did wrong?
sure, yep. Yeah, you can come up and I'll try to. I have about half of it memorized. Wow. But another thing when you're doing, well, I've spent probably 200 hours operating this wheel. Yeah. It's you'll memorize it too. There are also, like, on the big worksheet, there are also the extra mathematical tricks where, like, when you're adding up an entire column, you learn to recognize, like, cast out Q's and all sorts of tricks like this. Okay. So yeah, don't do that. Let's see. I'm just going to kind of spot check all of the ones that I do have memorized and see. It's at 9. 8S. Didn't we see that before? T, R. Wait, I see L plus Z. You have L plus Z equals 8. I'm pretty sure that L plus Z equals A. Let me check my, so that is at least one mistake. Yeah. Yeah, L plus Z equals A, right? Because L plus A equals Z, which is my baby's name. So that's what you got. Yeah. Yeah. Thank you.
So, so this, what we're doing here with these worksheets is just one part of a larger process of trying to generate our own wallet all by hand. And this would kind of be a final step to check that you've calculated everything correctly. Is that right?
So this is where this fits into a wallet process is that when you're setting up your wallet, in order to receive coins to it, you need to generate addresses. And at this point, you need to involve a computer. So you can, initially, if you want to generate your coins by your seed by hand, you can do that by rolling dice. And there's no wrong way to do that because it's just unstructured random data. So the checksum that you're adding, that you can add by hand, is just adding extra redundancy for later. But initially, there's no wrong way to generate an address because it's random and unstructured. And then if you need to generate addresses, right, you're going to have to involve a computer, so you do that. But then after that, if these are kind of long-term coins that you're receiving, then you would maybe destroy the hardware wallet that you use to generate the addresses or something like that. And at that point, the only copy of your secret is the one that's on paper. And then, or in a crypto steel or something like that. And where this process comes in is if that's your only copy and you don't want to make a new electronic copy, then you use this worksheet to check its integrity. And the point of this, so you might be thinking, well, if it's in a crypto steel, which is in a tamper-proof thing, like how could it change? Like obviously it is correct. I see the logic of that position, and yet you really want to know that like on this day 6 months ago, you checked and it was there and it wasn't tampered with and it's correct, right? Like it's really nice to have that ongoing assurance over a long period of time.
Data can get corrupted in all kinds of ways,
yeah,
basically.
Yeah. So one thing is, there's a non-trivial chance that when you loaded the crypto steel, you used the wrong tile somewhere because the crypto steel tiles, for some reason, some of them have different letters on the front and back side, which is insane, but some of them do. Another possibility, some of them are just hard to read, right? The way they're stamped, maybe they didn't quite get stamped hard enough, and it turns out they're hard to read. And then, like, if any extreme thing happened, if they get really hot, that could also make them hard to read or something, right? I mean, they're supposed to be able to withstand a tremendous amount of heat, but you can read Jameson Lopp's blog for.
So, reaching AN at the end of this confirms that it's a valid BIP32 address, or what did you?
Yep. So reaching AN.
It confirms that it's valid, and not that it's necessarily the one derived from what you started with.
Yep, exactly.
Okay.
So what it guarantees you is there is not exactly one error. There could be two or more. And if you do the full checksum worksheet, it will guarantee you that there's not exactly 1, 2, or 3 errors, but there could be 4 or more. So you get more with a bigger checksum. It guarantees, well, it indicates that if there are random errors, any number of random errors, then with 99.9, with 1,023 out of 1,024 probability, you wouldn't have gotten AM. So it's very strong evidence that there's not a string of random errors. Now, it's very easy for an adversary to generate bad errors. So if I wanted to tamper with your data in a way that the integrity check would still pass, I could do that as an adversary. So this can't deal with tampering. You would need like a Mac or something for that, and I don't have a hand-computed Mac in mind. But that's what it tells you. It guarantees there's not a small number of errors, and it gives you high probability that there's not a random number of errors.
But so you are saying it is actually possible that invalid addresses can arrive at AN at the end of this?
Yep, exactly.
That's
Every
very
single
low
valid
percentage.
address will give you AN at the end of this. Yep. It worked? Cool. Hey, excellent. Cool. Wow, that made me look so good that turned out to be true. Yeah. Right. Yeah. That's. Yeah. Yep.
So I have a question. If you actually did this and you detected that there was a problem, how would you know how to fix it?
In the case of the
No,
quick
I got
checks,
this done.
to fix it, I would just get another copy of the quick check sheet and just fill it out again, and then just compare line by line. And hopefully you won't make exactly the same mistake again.
Sorry, no. What I meant was you're trying to validate an address that you have in cold storage.
Yep.
So you validated it successfully last year,
Yep.
the
But
year
this
before,
year- yeah,
the
this
year
year it's not.
before. This year it's not. Now what?
So, number one, redo the worksheet, because hopefully you just made a mistake in the calculations or you copied it wrong. But maybe you didn't, right? Like maybe it is actually corrupt. In that case, you would switch from doing the quick checks to doing the full worksheet, the full diagonal one. So rather than taking you 10 minutes, it's going to take you an hour, but okay, you do that. At the bottom, well, it's cut off here, and it's not. Let me actually switch to the real one. Let's do events tilde media docs codex. All right, all left. Fine. Pivete. Très bien. All right, at the end, you should get secret share 32 here. That's reasonably big. You will not get secret share 32, right? If the data is actually corrupt, you will not get secret share 32. Now, what you can do is take the value that you do get. What that represents is the residue of your data modulo the generator. The correct data, whatever that happens to be, its residue is 0. So in principle, this non-zero residue, or this non-secret share 32 residue, has no information about your data. So you could plug that into an electronic computer and say, what is the error pattern corresponding to this output that I got? If you don't want to do that, there's a lookup table that I have somewhere that you can use that for all of the, there's like a couple thousand possibilities for 1 or 2 errors. You could just look up the value in this giant lookup table, and it will show you the error pattern. And what the error pattern will look like is it will say at column 6, you need to add P, or at column 20, you need to add F, or whatever, right? All it knows is the offset. It doesn't know the real data, it just knows the offset from whatever you put in and the column that that offset goes to. So somehow or other, you learn the error pattern, and then you double back and you offset your data with that error pattern, and then you redo the worksheet from there, and it should work out.
And you're saying then you'd get the correct address.
Yeah, and then you will get the correct address, assuming that you have at most 4 errors in your address, right?
Is the other approach to just require that you periodically do a transaction of the address to validate it?
So yeah, with addresses, you're correct. You shouldn't error correct an address. An address, if it doesn't pass, you should just request it again. Say something went wrong, just give me a new address. With secret data, though, right, the real secret has money on it. You can't just regenerate it, right? So you might, with secret data, you kind of have to make do with what you have. And in that case, you want to error correct it and then see if you get the correct data. And if you don't get the correct secret, even after error correcting it, then you can use something called a list decoder. And there, like, you can no longer use pen and paper, but you can use what's called a list decoder to generate all of the possible secrets that are farther and farther away from your original data. And then you generate addresses from those and compare those to the known addresses that you've received coins at. And you just run through the list decoder until you find one that generates your addresses that has your money on it. And if that doesn't work, then you need to run it for longer.
Question.
Yeah.
So supposing you run your data through your algorithm and you do not get secret share 32, so you know there is some sort of an error in it. Would it be possible to perhaps not quite reverse engineer, but to try to get the correct data from the ending value? You know you're supposed to get secret share 32. Would it be possible perhaps to try to work backwards from this and to try to figure out where you went wrong?
or what the correct value for it should be?
Yep. So on the last, let me actually go back. On the very last, in the last 13 characters of this, what you're doing is you're just adding a bunch of data. Starting from your original data, you're adding a bunch of other stuff to get secret share 32. So if you have a mistake in the last 13 characters, you can totally just like add backwards. And it turns out in this field, addition and subtraction are identical, so you can literally fill in secret share 32 and then add everything and compute what the, and if when you're generating a checksum, that's what you do. You write secret 32 and add backwards. So yes, you can definitely back compute for the last 13 characters. But then going back further, you need to undo the modular reduction. And I don't have a good reason as to why, like, in principle, that's possible, right? Like the properties of the error correcting code are that there has to be a unique way for you to do that. But if we forget for a second that we've got this nicely structured error correcting code and think about what we're doing, right? We're trying to find a large string that when reduced gives you a small string. You can see there's a lot of possibilities and there's no a priori reason to pick one. And so it's not really possible to back compute past the last few columns. Yeah, but it's a good question, and I've tried this for a while, but I haven't gotten anywhere.
Well, I suppose you can try to brute force it.
Mm-hmm.
If there's a bunch of possibilities, you can try doing all of them.
Yeah, for sure. But if you were to try to brute force, at least in the naive way, there's kind of an exponential blow up in all of the more characters you go back, the more choices you're going to have to make to go backwards. And I think you'd be better off mathematically, you'd be better off just trying to do Brillicant Massey or something, even by hand. But I guess if all you have are the tools in front of you, right? You just got the workbook and you're following the procedures and you're not, you don't want to like peel back the layers and figure out the underlying mathematics, then yeah, you could try brute forcing. But I don't think, you're not going to get further back than 1 or 2 characters, I think, doing that. And it's really annoying to use the lookup table backwards, which you'd have to do. Let me zoom out. Let me find the lookup table. Oh, sorry, I'm navigating people. There we go. So yeah, you can kind of imagine trying to use this table backwards, right? Where you're like, okay, I have this 13 character string. Let me search this giant thing and figure out which 2 characters would have given me this string, right? And actually, you don't even have a string that's in the table. You have a string that's similar to something in the table, and you're trying to find all the similar looking strings to go backwards. It's, I don't think it's feasible. Maybe. I'm not going to say it's impossible because this is so open-ended that like there's probably something there. But I spent a lot of time trying to color code random things and trying to find shortcuts. And
Apparently, like you can do some dimensional analysis on faces, and like artificially generated them from entropy, and there's quite a few bits in it, and people are able to tell faces apart and remember them. So you might be able to have a lookup table with a bunch of random faces in it. It'd be a bit weird, but you might be able to very quickly find the face in a 2-dimensional.
Right. Yeah. Yeah. And if you give all the faces names, then you like tell yourself stories about all these AI generated faces. Yeah, there's some cool like cyberpunk user interface design in there. I'll give you that. Oh, yeah, we've got a question up front end. In the
I know that checksums are used on credit card numbers. Is the algorithm similar where you add up the numbers and you expect to always arrive at the same result?
Yep.
Okay.
Yeah, I don't know the credit card checksum algorithm, but I do know the barcode one, which is kind of neat. There you interpret all your numbers as numbers modulo 11. It's weird. You've got 10 digits, but 11 is a prime, so it's better to do that. So you add the extra digit x in there as just like this bonus number. And then you add the first digit, subtract the next, add the third, subtract the next, and mathematically you're just multiplying by a -1 on each iteration. And then the result has to equal 0. And so you add this extra, the single extra check digit on a barcode that gets you that. And I assume that the credit card checksum algorithm is the same. Yep. This is kind of universal to all linear codes, which is by far the broadest class. So not just BCH codes, but almost all error correcting codes used in practice are linear codes that behave this way.
I guess I just thought I'd seen somewhere, reading some documentation somewhere, and I think maybe it was in Understanding Monero, but they said that the end of a wallet address, the last 2 digits were maybe a checksum, and you would assume that those are not always the same, because why would you even put them there? So are some checksum algorithms, they work where they don't always yield the same result at the end to like signify it's valid?
No, the distinction that you're making here is that the 2 characters that appear in the address and the 2 characters at the end of the worksheet are different. So the 2 characters that appear in this worksheet never appear visibly outside of the worksheet. So that's just like an internal part of the computation. Yeah, and getting those crossed is a pretty common, natural thing to do with these worksheets that we've tried to avoid. Yeah. The terminology is also not great. Like one is called the checksum and one is called the residue, but people sloppily use the same term for both. And
Maybe I was sleeping at the beginning. So you start with nothing, other than dice, and you roll the dice, assuming they're the bubbles, and you've already accommodated. You're kind of trusting your dice. You roll a bunch of things. You get your secret number, right?
Yep.
And then, did I miss how you derive your first address from that?
no, I kind of avoided that for this workshop. So there's,
Okay.
yeah, so
We're
2
verifying an address that we know it is a valid address,
Yep.
not how we got to that.
Yep, exactly. So
Okay.
if you somehow had an address without a checksum and you were producing the checksum,
Right.
for one thing, you can't use a quick check worksheet. You have to use a big diagonal one. And then there's a slightly different process for using it, where you fill in the results you want at the bottom, and then you like back compute the last few characters. But
Is this explained in the handout and the book?
yeah, this is explained in the booklet.
Okay.
Yeah.
Okay. So
Yeah, but,
very good.
yeah, in this case, what we're doing now only works because we already have a valid checksum.
Right. We kind of skipped to step 3.
Yeah.
Skip 2. Okay.
Question at the back, and then front.
Hey, thanks for taking my question. What are you looking to see in the next 5 or 10 years in Codex32? Is your end goal to have it merged into Bitcoin Core? What challenges would you see? And then maybe another side of that same coin, have you heard any reasonable criticisms for Codex32, why it would not be implemented or adopted?
Yep. So the first question, like, do I want to see it in Bitcoin Core and other wallets? Yep, for sure. But it's a whole nother import format that's different from the seed words that people are familiar with and so on. So there's a bit of work that needs to go into that. One big thing is that this format, uniquely except for slip39, supports error correction and error detection and all sorts of stuff like that. So for a wallet to support this import format is not only, if it were as simple as just like, if it's valid, take it, and if it's not, reject it, the way you do with BIP39 words, then that would be easy, and like we could already, we could deploy it on 1 million wallets. But thanks to a whole bunch of work from Ben Westgate, we actually have a fairly long document of recommended user flows for wallets to import seeds and to import multiple shares and reconstruct a seed from them, and how to highlight mistakes if the wallet believes there are mistakes that be corrected, and how to give user feedback and stuff like that. So it winds up, wallet integration winds up being a much bigger job than it obviously would be, because there's these extra features related to correction and extra features related to secret splitting and the way they interact. So there's a bit of work left to do there on the implementation front. But we have a pretty clear idea of what we need to do, and we're chipping away at it. And the second question about criticisms. So one is, the biggest criticism I would say is that this is basically the same as SLP39, except we have a slightly longer checksum that can correct more errors. Okay, that's worth something, but SLP39 is already pretty good. And SLP39 uses a set of seed words and encodes your data as a bunch of words rather than encoding it in this kind of compact best32 format, which has pros and cons, right? So encoding as words is less efficient, right? It takes more space, but it also gives you a bunch of free redundancy, right? If you misspell a word, you can probably mentally correct the word, right? Without having to do error correction, so that's nice. SLP39 also, our Codex32 seed format has some metadata encoded on it, and which is like preserved by the secret splitting and all sorts of neat features like that. That's nice, but like, is it enough to tell people not to use SLP39? Like, is it fragmenting the ecosystem? That's really been the biggest thing, is that it's very similar to SLP39, except it just showed up on the scene later, and like already SLP39 has struggled to get adoption, so why should this get a delay? Is this just causing more fragmentation than it's worth? Now, SLP39 can't be done by hand. Like, this is really the reason for all this to exist, is that it can be done by hand. If we couldn't do it by hand, we wouldn't, like, the technical improvements would not have justified doing this project. And then there's a kind of sort of criticism. There's another project called Penlock you might have seen on the Bitcoin dev mailing list, called penlock.io, which is similar to this. It uses a different error correction scheme where it sort of independently checksums small clusters of characters so that you can basically correct up to an unlimited, basically for every 3 characters, as long as 2 of them are correct, you can fix the third one, is the way that Penlock works. So in total, you can correct a much higher number of errors, but they can't be clustered too closely, is kind of the benefit of Penlock. And so there's like this open design space around these sorts of schemes. And like, did Codex32 make the right trade-offs? Another benefit of the way Penlock does things is that this addition wheel is much simpler for Penlock. Here it's like we've got 1,024 characters, and you got to cut out 32 little windows. The Penlock addition wheel is much simpler. But we can correct burst errors, and they can't. And I mean, that's not quite a criticism, but it's not. There are a bunch of trade-offs that we made in designing this, right? And it's not obvious that these are the best ones. But in terms of criticisms, right, the 2 big ones are, well, number 1, BIP39 is 1. Deal with it, and I just reject that. And then the other is that this is so similar to SLP39, and like it's an uphill battle and possibly not worth it. But I would argue that the hand computation makes it worth it. Yeah, up front.
So, is there? Oh, thank you. Is there? What are these called again?
Volvels.
On the volvels, is there any is there any structure to the back page, or is it really just a lookup? Is it just a lookup?
It's really just a lookup table, yeah. So in the full scheme, there are 3 wheels, 3 volvels that you use. And the other 2 have a bunch of neat structure, which allows them to not even have windows to cut out. They, in the picture, I think there was a picture, yeah. You can see the other 2 are, all the symbols are visible at once, and you're rotating them relative to each other. And the reason is that the underlying operation there is cyclic, in a sense that like cashes out as being a literal circle. There is a tiny amount of structure in the addition wheel that would allow us to divide the number of things to look up by 2, and like reusing an element twice. But in order to do that, we would have to scramble. So on the outer wheel, we have the alphabet in order, so you can search around. We would need to reorder that in a way that's not very natural, and that makes lookups way slower, and we decided it wasn't worth using the extra structure. So yeah, it really is, yeah, when I first encountered these, I'm like, wow, this is like brilliant, but it really is just a lookup table. But the upside of that is that you can use this, so I'm obviously going to make one for like the 12 times tables and stuff for my kids and whatnot. It's very easy to modify this for all the other lookup tables in your life, right? So.
you could halve the number of elements on this lookup table as well, just because it's addition, so you've got every combination in here twice.
Yep. Yeah, there's a couple ways to think about it, but I think that is equivalent. So like A plus C equals 9 and C plus A equals 9. Those are both true. Yeah, so there's like clearly some redundancy there. But yeah, is it the same? I think that is this. So the actual redundancy that we're exploiting, I think, is that A plus C equals 9 and C plus 9 equals A. That's kind of a neat thing that you'll notice if you keep playing with it. So the redundancy where A plus C equals C plus A, I haven't found a good way to exploit that. It really seems like you should be able to, right? But I haven't found a way that we can make a smaller wheel that way. But there's an additional redundancy, which is that A plus C equals 9, and you can rotate the plus and the equals. So C plus, so like those three things together, you can put a plus and equals however you want in there. Yeah. I mean, the group operation has
So-
order too.
No, so the way you do that is you just halve the number of entries on the wheel, and when you're adding two numbers, in this case A and C, you always take the lower number from the top and the higher from the bottom.
Yep, you
And
can
if you
do
it
that.
that way, then you can halve the size of the wheel.
Yep, you can do that, and you can delete half the entries.
Yep.
But you can't. Oh no, actually, you can't do that. And the reason
It will work.
it's difficult to do. So imagine you're adding A and C, right? You say, okay, well, we always put A at the top and C at the bottom. Well, the C at the bottom is actually printed on the front wheel, right? And it needs to be carried around as you spin it. And I can't make the C go away when you're adding A, but not go away when you're adding D. Do you see what I'm saying?
Correct. As long as you do it in that order, you'll be fine. As long as you don't try to do a C-A, you'll be okay.
So I can erase the entries, and then sometimes blanks will show up. And that might be helpful. But you would still have to cut out the same number of windows, and everything would have to be the same size. Right.
You can actually reduce the number of windows by 1.
Okay, I think that's true. Okay. So yeah, there's I mean, that's not bad, right? I mean, that is a 3% reduction, which if we can make the windows bigger, that's a cool thought. I might play with that and see if it turns out to be practical. So thank you.
So are we adding elements from basically like a base 32 integer system?
Not
And then
quite.
taking modulo? Okay.
Yeah, it's not just numbers modulo 32.
Okay. I'm trying to understand why Q doesn't do anything. Like why Q returns the same thing.
Yeah, so the answer is that Q is 0, right, in this field. So even though it's not the numbers mod 32, it is an entity with a 0 object. You'll also notice that every number plus itself equals 0. You can look up like 9 plus 9 is Q, and C plus C is Q, and so on. And that's something that wouldn't be true if it was just the numbers mod 32, right? Because 16 plus 16 would be 0, but every other number would have its own double. And yeah, I don't know of a good way to describe what this field is. It's a pretty weird construction that's due to Galois. Yes, yeah. Yeah, so under the field that we're working with is the 32 element field, but we have polynomials over that field, and the space of polynomials is much bigger, right? That I think is what you're getting at. Yeah, and we treat the polynomials independently. I don't think that's me. Cool. So I should mention that the Atlanta BitDevs is happening at 6 o'clock, which is in about 20 minutes. And it's across downtown. It's about a 15-minute drive, I think, at a place called BitLab. You can look up. Oh, no. Manuel's Tavern. Okay. All right. Then I will look up where that is. Is it still, how far away is it? Okay. Okay. 20 minutes by car? Okay, cool. So if people want to get there on time, you're welcome to file out, and I won't be too bothered. You're also welcome to hang out, of course, and keep working. Let me tab through the rest of my... I don't have a lot. Yeah, so let me quickly end with just like a couple future work slides. Yes, I see people sitting down. Hi, Polly. Go ahead and pack up and stuff. But all right, what do we still have to do? Implement error correction on the website. We also have to finish it in the Rust implementation, do it in C and stuff. It's not too bad once you've got it. And that will let us do hardware wallet support, which is really like a really important goal of this, right? Is that you can actually use it with real Bitcoin equipment. We've also got a bunch of work on the PostScript. I keep talking about doing handwritten PostScript. In fact, I have been maintaining my own personal fork of this repo that I maintain. I maintain both the fork and the original repo that has all these artistic changes. And the way that they're implemented right now, and the reason I can't merge this in is that my co-author won't let me, because all the artwork comes from Inkscape SVG files that I converted to SVG using Inkscape, or they came from Photoshop or something. I converted them from SVG to PostScript, so they are together like 100 times as much code as all of the rest combined. It completely swamps all of our beautiful handwritten code. So we can't unconditionally pull it in, because if you're worried about backdoors, right, it's going to be in the Dragon picture somewhere. So instead, I have it subbed in by using PHP. And so I have this PHP PostScript polyglot that has like extra pre-computation or pre-compiling stages and like a shell script to do it. And I mean, PostScript is not a nice language, but there's a real prejudice against PHP that I feel PostScript equally deserves, but my co-author disagrees, so he won't let the PHP in. So instead, I have to rewrite the PHP bash crap in the Nix language, which we are going to use instead. And the Nix language is also an awful language in different ways than PHP, but okay. So I've got to convert it to Nix, and then it has to go through a bunch of code review, and like, I don't know, it's a process to get all the artwork in, as well as stuff like the typesetting engine. So in the early pages, you can maybe see I've got these nice drop caps and like all that nicely written text. PostScript doesn't have facilities for flowing text. You can't like do line justification where they're all equal width. I had to write my own typesetting engine in PostScript and then write a bunch of code to flow the text. So I've also got to get that merged in. That's a lot of code. It's not as bad as the art itself, but it still has to go through review. And I'll merge that stuff in. And then, yeah, I would like to implement error correction by hand. That I think is possible. I don't think it's too bad, but it's certainly not trivial. And there's a lot of work we have to do there. And then I'd really like to be able to do the EC stuff by hand, but that seems really, really hard. And actually, I will show one last slide from the middle of my thing here. So in particular, I want this slide. So to do this EC multiplication that I'm talking about, to give you a picture of how hard it is, naively, right, you've got a 256-bit number, and you're trying to multiply that by an elliptic curve point. So one thing you can do is just binary decompose it, right? And so you have your generator and 2 times the generator and 4 and all your power of the 2. You pick the ones corresponding to 1 bits and add them together. It's 128 additions. Well, you can do that better than that. Rather than having 256 powers of your generator, you generate a whole pile more of them, and you can make it so you just look up, I guess, 52 curve points in a giant lookup table with 400 pages in it. And by the way, if you're worried about backdoors, if you do this way, and a malicious person gives you a tome that has powers of a low-order curve element, and then you use that, and then you provide the output to that person, they will learn some bits of your secret. And if you then accept another tome from the same person and spend 3 months working through this, and you go through this interaction multiple times, it will take most of your natural life, they will be able to steal your coins. So there's the back door. So okay, we can get this down to like 50 things with you know, tome punk. There's a whole genre of tome punk fan fiction that we're writing about this.
If you're boiling tea after each of these bits, is that a side channel timing attack or?
So yes. So one thing I mentioned in my rambly slides is that I think that we don't need to care about constant timeness for this, right? So it is true. Like if you're taking multiple days to do this, like anybody can tell like how many days it took you to do this, right? And there is like actually a lot of leakage there, but you're also not doing it in real time, right? Like people don't know when you started. People don't know what you're in the middle of working on, right? So I think the constant timeness probably doesn't matter because you can't do any of this in real time. But continuing, okay, so we have 50 or so of these additions. Each one of those requires 11 multiplications modulo a 256-bit prime. If you can reduce that, that would be awesome and would significantly speed up all of the electronic implementations of these. And DJB and Tanya would like to hear from you. They have a database called EFD, which is the Efficient Formula Database, I think, which has, for all different categories of elliptic curves, the most efficient ways to do elliptic curve addition in terms of multiplication. 11 is the best, okay. Each of those multiplications, you're doing multiplication modulo a 256-bit prime, so you've got a bunch of carries to worry about. You've got to do Montgomery multiplication, which is at least twice as much work as a normal multiplication, which in general is quadratic, although you can reduce it. You can use like Karatsuba and generalizations to get it less than quadratic. But each of those, pretty much no matter what, we think each one takes multiple hours. We've never done it, right? It's so time consuming, we haven't done even a single scalar multiplication. But let's say it's 4 hours, right? So, okay, so times 11, that's 44 hours to do a single elliptic curve multiplication. So that's a full work week doing nothing but like filling in these workbooks. And then you have to do that for 50 weeks. So that's a full year, and you can't make any mistakes. A full year just like working full time. So this is where we're starting from. We have, I'm just going to throw a slide up of like half-baked ideas here, but not elaborate because we're low on time. But you can read these and speculate.
Yeah, I had just a comment on the PHP and the PostScript thing. So if you're using PostScript to output like some PDF, you can use also Typist, and it's written in Rust, and you can do like Rust stuff inside of Typist, and it's fully open source, and you can use that maybe to get the like PDF and the calculations for the lookup tables in an easy manner that is Rust interoperable as well. I don't know if you ever heard of Typist.
No, I'm not aware of it. So yeah, maybe I'll try to remember that, or you can ping me or file an issue or something. That might be useful. All right, I will wrap up there. I will be around. Feel free to bug me. I haven't decided whether or not to go to BitDevs. I know it's like right now, but I'll decide as I'm walking. Oh, one more question.
Where do we buy that book?
Oh, where can we buy the book? You can go to store.blockstream.com, and let me check that this is a true statement. .com. Oh, if I am connected. All right, you might just have to believe me. But on the Blockstream store, it's called Codex32. Oh, there's something happening. Yeah, I think it might load, but all right, hopefully it does on the way out. Cool. So thank you, everybody, for coming. Hope you had fun.